consider this problem. We have an LTI system and its impulse response is as shown here by the red function. It's h of t. And the input to this LTI system is x of t, which is a pulse of height 2 from time t equals 2 to t equals 4. And the expression for h of t, based on the graph, we can find this expression. It's a line with a slope of 1 by 3, and there is no y-intercept. And this expression is valid from time 0 to 3. And our goal is to find the convolution integral, which will give us the expression for the output of the LTI system, y of t. And the first step in convolution is replace the variable t by tau. So what we're going to do is draw a similar graph, but we're going to replace all t's by taus. So that's the first step. The second step is we are going to time reverse h of tau. So we don't make any changes to x of tau. We're only going to change the red function. We're going to reverse it, flip it about the vertical axis. So let me erase that and draw a reversed copy of h of tau. So this point is -3, and this point, the other point is 0. So this is h of minus tau. So those are the first two steps in convolution. We replace t by tau and we apply time reversal to h of tau. And then the third step is apply a shift of t to h of negative tau. So let's draw another figure or copy this to show how the two functions interact as we apply a shift of t to h of minus tau. And we need to consider all shifts, all values of t. T represents the shift, and t could be from -infinity to +infinity. So we need to consider all values of t. That means we start by applying a shift of -infinity. That will bring our signal all the way to -infinity, and we will gradually increase the shift value and until we get to +infinity. Okay, so any negative shift, any negative value of t would move the red function to the left. Any positive value of t would move the red function to the right. And as we move the red function, we should keep track of its front and back ends. So the point that is initially at 0 becomes t as we shift it, and everything else should be with respect to that. So that means the point that was initially at -3 becomes t minus 3 as we apply shift to the red function. Okay, I'm going to group this. All right, now let's see how many different ways the two functions interact as we move this red function from -infinity to +infinity. So when we're at -infinity, we don't see the function. As we slowly increase the value of t and get to t equals 0, we are here. So until this point, there is no overlap between the non-zero portions of the two functions. And we keep on increasing t. And when we apply a shift of t equals 2, this is what the graph would look like. And at this point, we start seeing some overlap between the red function and the blue function, right? Increasing t beyond this point will just increase the overlap. So this point, t equals 2, is an important boundary value. This is when the partial overlap between the two functions begins. And so we increase t further, and we see that the overlap will keep on increasing until we get to this point. And this is the point when we start seeing full overlap. This graph right now corresponds to t equals 4, and increasing t beyond that will keep the full overlap, right? So we increase t further. It will look like this until we get to t equals 5. And t equals 5, this is another important point that we should mark. And after this point, if the value of t is more than 5, what happens is the overlap will decrease. So we start seeing partial overlap after t equals 5 until this point, which corresponds to t equals 7. This is when any overlap between the two functions stops. And after t equals 7, we see no overlap, and this trend will continue until infinity. So based on what we observed, we will mark some important boundary points. One was 2, then 4, 5, and 7, and we'll always add negative infinity to the front and plus infinity to the end. And based on these boundaries, what we're going to do is split the total range of t, which is from minus infinity to plus infinity. We're going to split that into several regions. The first region is when before any overlap occurs, and that is from negative infinity up to t equals 2. And the second one is when we see partial overlap. That happens from t equals 2 to t equals 4. And then region 3 is when we see full overlap. And then region 4 is when there is partial overlap again. And in the final case, there is no overlap. The first one, no overlap, happens in the fifth case as well. The second one is partial. Happens in the fourth case as well. And then the middle one, we saw full overlap between the two functions. When we say overlap, we're talking about just the non-zero portions of the two functions. And the first two steps of convolution were, again, replace t by tau and apply time reversal to h of tau. And the third step is apply shift to h of minus tau. Now what we need to do is the remaining two steps, which are multiply x of tau and h of t minus tau, then integrate the product. And we're going to do those two steps, multiply and integrate. Those two steps 5 different times because we have 5 different regions to consider. So consider one region at a time. For the first one, let's draw a picture that represents this first region. Okay, and this graph represents the first region. There is no overlap between the two functions, and that means the product between these two functions is 0. So if we consider the convolution integral, negative infinity to infinity x of tau, h of t minus tau d tau, the product is 0. And as we integrate this 0, we get a 0. So for the first region, we get a 0. Now let's consider the second one where we saw partial overlap. And we're going to draw a graph to show how the two functions interact. Let's draw it like this. And let me shade the overlapping segment. So from t equals to tau equals 2 up to tau equals t is where we are seeing the overlap between the non-zero portions of the two functions. So that's an important range that we should keep in mind as we evaluate the convolution integral. Because the lower limit of the convolution integral, it is when the non-zero portion begins, non-zero product begins, and that is 2. And the upper limit is when the non-zero product ends, and that is t. And then we need an expression for x of tau. X of tau in the shaded segment, x of tau is just 2. H of t minus tau is a line in that segment we're considering in the shaded region. And the expression for that line is, we can go back to the original expression for h of t, which was t by 3. And since we need h of t minus tau, we can just replace t by t minus tau. So that is the expression for h of t minus tau. Let's write that here. And then we integrate with respect to t, with respect to tau. So 2 by 3 is a constant, and we get t tau minus tau squared by 2. And we apply the integral limits to the t. And when we evaluate this, we should get 2 by 3 t squared by 2 minus 2t plus 2 after some algebra. So this is the expression for y of t in the second region. Now let's consider the third one. And we're going to draw a graph for this region as well. The graph should show maximum or full overlap possible. And then I'm going to shade the overlapping segment. The shaded green region is when the product between the two red and the blue functions is non-zero. Okay, now let's consider the integral, convolution integral. The lower limit of the integral is when the green section begins, and that is 2, and the green section ends at 4. That is our upper limit. X of tau is still 2. H of t minus tau is still t minus tau by 3. And then, again, we integrate with respect to tau, and we should get this, but with different limits. And as we apply the limits, we should get 2 by 3 to t minus 6. Okay, now let's consider the fourth region. The fourth region is from 5 to 7, and we see partial overlap. And this graph, the graph looks something like this. And I'm going to shade the overlapping segment again. So the overlap, it begins at the left end of the red function, which is t minus 3, and it ends at the right end of the blue function, which is 4. That will help us determine the convolution integral limits. So the limits are going to be, the lower limit is the left end of the shaded green section, which is t minus 3. And the upper limit is the right end, which is 4. And we still have 2 t minus tau by 3. Those are the expressions for x and h. And now integrating this, we get 2 by 3 t tau minus tau squared by 2. Again, this part is the same, but the limits are different. T minus 3 to 4. And with these limits, we should get 2 by 3 minus t squared by 2 plus 4t minus 7 by 2. And then we need to consider one more region, which is region 5. The graph for region 5 looks like this. This is when there is no overlap. The red function is all the way to the right of the blue function. And since there is no overlap, the product is going to be 0. And since the product is 0, if we integrate the product, it is going to be 0. So we found the expression for y of t for each of the 5 regions. And now what we're going to do is collect our answers for all 5 regions and copy it here. So here I have copied our answers for each region. And this is our answer, but we can do sanity check before we stop. Okay, so the first thing we're going to check is the range of various functions. So range of x of t, it is 2 to 4. Range of h of t is 0 to 3. So based on this, what we should be able to tell is that the range of y of t should be from 2 plus 0, which is a 2, to 4 plus 3, which is a 7. And that is exactly what we got. From 2 to 7 is the non-zero portion of y of t. So the first sanity check, it passed. Now the second one. Second test is boundary values. So there are several values of t that are included in 2 different ranges. For example, 2 is included in the first range and the second range as well. So when we evaluate y of t at t equals 2, we should get the same answer whether we use the first row or the second row. So if we use the second row, that means we evaluate this expression at t equals 2, and we get 2 by 3, 4 by 2, minus 4 plus 2, which is a 0. And if we evaluate y of t at t equals 2 using the first row, we get a 0. So we get a match. That is good. And let's check the other boundary values. The second one is 4. If we evaluate the second row at t equals 4, we get 16 by 2, 8 plus 2. And using this row, we're going to get 2 by 3, 8 minus 6. So we have a match again. Let's try 5. Using the third expression for 5, we get 10 minus 6. Using the fourth expression, we get 2 by 3, negative 25 over 2 plus 20 minus 7 by 2, which is 20 minus 16. If we, we got the same thing for 5 also. And the final one that we need to consider is 7. If we use the fourth row to evaluate the value at t equals 7, we get 2 by 3, negative 49 over 2 plus 28 minus 7 by 2, which is a 0. If we use the final expression to evaluate y of t at t equals 7, we still get a 0. So all the boundary values also checked. So the expression, we didn't find any error in when we did the sanity check. So this is our answer for y of t.